to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Say I'm dangerous 'cause I broke all the cages. No, I won't sit and take it. No, no. They left me for dead, I guess I'll never learn. Every time I break, there's just more pain to burn. They'll never, never, never learn. Till the battle's won, till kingdom come. I'll never run. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Say I'm good-hearted, but I'm just getting started. Got my eyes on the target. No, no. Till the battle's won, till kingdom come. I'll never run. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, they'll be calling me royalty. They'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, calling me. They'll be calling me royalty. Best to give me your loyalty, 'cause I'm taking the world, you'll see. They'll be calling me, calling me. They'll be calling me royalty.
एकछिन है 2 फिट बस्नु चाहिँ राख्नु छ गाह्रो भएको फुटहरू पटक्कै फिट गर्थेँ मैले नगइसक्यो यार के फिट गर्थेँ मैले ट्राई राम्रो आएन त या के हो यो यस्तो के हो यस्तो कस्तो आउँछ ठिकै छ नि यस्तो के गर्नु मिल्दैन र यो फरक पर्दैन यस Okay. recently भएको यो मे अप्रिल मे जुन जुलाई मेमा 31 अप्रिलले छ जस्ट बेबी सिक्स छ्या खानु destination and poster.
Remember, descriptive statistics are as simple as, suppose I label them with numbers 1, 2, and 3. As the sample size increases, the information you have to work with increases. The problem is, when you computed the mean here, as you've done in this formula, you've already used some information, have you not? You've used what we say is at least We now turn our attention from descriptive statistics, that is, describing the data you have in hand, to inferential statistics. Inferential statistics are where biostatistics really helps to make your life much easier. What we're doing in inferential statistics is not merely describing the data we have on hand, but something much more profound and much more powerful. We're standing on the data that we have, and we're projecting to what's true in all the rest of the known universe. The core to inferential statistics is right there. It's making an inference. And the key idea here is a simple but crucial one. You're not supposed to be focusing on the data that you have in hand, because that's mere data. You're supposed to be projecting to the reality you're estimating. The difference between the pros and the rookies in dealing with inferential statistics are right there. The rookies get fixated on the data. The pros focus where you should on that estimate of reality. We're never just stopping with what we have, we're always estimating what that reality is in the world around us. Now, remember in descriptive statistics, how I said I got all the scores from the class, and I could then summarize them using mean, standard deviation, to represent the class as a distribution? That's what descriptive statistics is. If I was going to use inferential statistics to get a sense of the class, what I would do is give the class a test, but let's say I'm not able to talk to everyone in the class. Let's say instead I'm able to get scores from only 7 people out of a huge class. I take the scores of those 7 people, I add them together, and divide by 7. I compute the mean for those 7. That's my data. Now, crucial question. Do you believe the mean of those 7 is going to be, and I mean exactly the mean of the class as a whole if I talk to everybody? Well, the answer, of course, is no, of course not. But do you think it's going to be close, in the ballpark, a reasonable approximation? The answer to that one is yes. And right there, succinctly, you have what we're doing with inferential statistics. We're talking to some and making a projection to all. Now, you can talk about this using a host of different words. I don't care which words you use. I'm going to run through some word pairs here so you have a sense of what we're talking about. From some to all, from the sample to the population, or the one I like, from the data to reality. What we're always trying to do in our inferential statistics is, again, stand on the data we have and project to what that reality is. The key idea, your focus is not on the data as such, but only on the data as providing a base for that projection to reality. Now, this is important, because data is something that changes and is transitory. If I conduct a study and collect a certain amount of data today, I conduct a different study tomorrow, my data is likely to be different. The reality, though, we believe is stable. So it's that projection to reality, that stable sense of the world that we're always focusing on, not merely the vagaries of the data we collect. There's 2 ways we build this bridge, from the data we have to the reality we're trying to get a sense of. 1, confidence intervals. 2, hypothesis testing and p-values. please understand at the outset of our discussion, these are two alternative methods for achieving essentially exactly the same thing, building an intellectual bridge from the data we're starting with to that projected reality, which is our aim and our goal. We're going to start our conversation about inferential statistics by focusing on confidence intervals, and for a very basic reason. Because confidence intervals are by and large how statistics are done. In medicine. Almost any medical journal article you care to look at, if there's data involved, if you really don't understand confidence intervals, then you don't understand the article. So let's talk about confidence intervals. Now, the idea of a confidence intervals is pretty straightforward. It's an idea you probably have intuitively before I started talking with you today. Confidence interval is just a recognition that reality is not a single number, but reality is going to be around that given number. We say, let's say a class starts at 10 o'clock in the morning, but you come strolling in 2 minutes after 10. Well, you're close enough. You're okay for that class, right? That's a confidence interval way of thinking. Or you're out on the highway, driving along, nice clear day, posted speed limit says 65. You're driving down the highway at 71 miles an hour. Cop pulls you over and gives you a ticket. Aren't you pissed at that? Aren't you angry at that? Because you kind of figure, most of us do, we ought to get plus or minus 10 miles an hour on the speed limit. That's a confidence interval way of thinking again. As long as we're within that specified range, we're okay. Outside of that range is something different. Now, all we really have to do to use these confidence intervals then is get a sense of how to calculate what that interval should be. We use formulae to calculate these intervals, but understand for a very pedestrian reason. Not because the formulas are any sort of pristine, God-given reality, but because they're consensual. You, with a set of data, would estimate the same reality that I would estimate with the same formula and the same data. The formula that I want you to learn, the one you're most likely to need on your exam, is given here in the yellow box on the slide. It's the mean, x bar, plus or minus z, times the quantity s divided by square root of n. Straightforward, fairly easy calculation, something they could easily do in the time limit of an exam question. Let's take some time and walk through and look at the pieces and understand what's going into this confidence interval of the mean. X bar is the mean. You know what that is. You knew what that was since probably sometime in grade school. It's the arithmetic average. Plus or minus, that simply means going equidistant above and below that mean. Mean is a pivot point. We're estimating reality as somewhere around that given mean. Z, let's hop over that for a second. Instead, let's first focus on what's in the parentheses. In the parentheses, we have s divided by square root of n. And that quantity, taken as a whole, is referred to as SE, or the standard error. SE, or the standard error. Now, look again at the word, standard error. This is error. And so, would you like this number, if you had a choice, to be large or small? Well, small, right? Because error is bad, and so having less error would be better. Notice, to remind you again, two things go into the standard error. S, the standard deviation, and N. And the sample size. Now let's think this through. Suppose we have somebody who does some research and they have a sample of 100 people in their study. Nice study. Suppose we have someone else that does research and they have a sample of 1,000 people in their study, much larger study. Who, in your opinion, has a better picture of what reality looks like? Sample of 100 or sample of 1,000? Well, sample of 1,000, right? Right. And so as the sample size increases, my picture reality gets better, right? Well, another way to say that is, as the sample size increases, my error should decrease. So we divide by n, because as the sample size increases, the error should go down. Now, why the square root of n? Well, that's obvious, because it's not a linear function. See, the amount of information, the value of the information I get when I go from, for example, 7 to 8 people in my sample, compared to when I go from maybe 1 million to 1,000,001 people in my sample, the value of 7 to 8 is much more than the going from 1 million to 1,000,001. And so since it's not a linear function in terms of the value of the information, square root describes that function very nicely. We use the square root function because it describes the fact that small increases in sample size at the low end matter much more than the small increases at the high end. In general, the issue should be intuitive here. As the sample size increases, my picture reality should get better, therefore my error should decrease. Let's think about the standard deviation. Let's do this by a simple thought exercise. Suppose I have a class, and suppose I give the class an exam. And I get the scores back for the exam, and I'm stunned because every single person in the class got exactly the same score. 76% for everybody, no exceptions, everybody gets 76%. Suppose I sample 7 people at random from the class, take those 7, add them together and divide by the number 7. I use the mean of those 7 to represent the class as a whole. In this illustration, do I have a good or poor representation of the class as a whole? The answer is I have a perfect representation of the class, because everybody got the same score, and so literally those 7 are as good as anybody, right? Hold on to that. Let's do the contrast. Suppose again I give the class an exam, but this time as I get the scores back, I find that everybody scores all over the map, from 0% to 100% scattered everywhere in between. Once again, I sample 7 people at random, compute the mean for those 7, and use the mean for 7 to represent the class as a whole. In this second instance, do I get a good or poor representation of the class? Well, comparatively, I get a much poorer representation. Well, let's translate what you just told me. You just told me that when the standard deviation is small, I have less error. When the standard deviation is large, I have more error. And so bang, S goes on top. Because as the standard deviation increases, the error should increase. 2 things go into the standard error. S, smaller would be better, and N, larger would be better. Now, which one of these 2 can I do something about? Which one of these 2 can I actually have an impact on as I'm doing my research? Well, I hope that's obvious. It's the sample size. This is why you always hear when you're doing research, like a drum beat, the conversation about the sample size, the sample size, the sample size, because this is quite literally your lever to reduce error. By increasing the sample size, we can reduce the error in this standard error. The standard error is telling us, in some sense, the quality of the data that we have, the quality of the estimate we're going to get from that data anyhow. And in this confidence interval, I want you to think about the standard error as what's giving us the interval. Z is giving us our level of confidence in our, the words again, confidence interval. Z is called a Z-score or a standard score. And let's pause and just do a brief vocabulary check, shall we? What is S? S is the standard deviation. Good. What is S divided by square root of n? That is the standard error. What is Z? That is the standard score. The point here is you better, as you're reading your question, pay attention to the second word. not just the first word. There's 3 standards. It's the second word that tells you what it is you're looking at. So let's talk now about the z-score or standard score. A z-score, a standard score, is a score taken from a distribution that we invented. We made up. We made it up to have the following simple, easy-to-use properties. 1, mean equals 0. 2, standard deviation equals 1. Why these properties? Because it makes it stunningly easy to work with. Look, mean equals 0. What does that mean? Well, it means any z-score with a positive number must be above the mean. Any z-score with a negative number must be below the mean. By seeing whether I have a positive or negative number, now I know instantaneously whether I'm above or below the mean. And that's handy. Standard deviation equals 1. What does that mean? It means z-scores are in standard deviation units. It means if I have a z-score of +1, I'm 1 standard deviation over the mean. It means if I have a z-score of minus 1.76, I'm 1.76 standard deviations below the mean. Z-scores are, once again, basically giving you standard deviation units. Plus above the mean, minus below the mean. This is really handy. Let's make use of this. In any z-score distribution, what percent of the cases fall between a z-score of +2 and -2? Well, that's easy. As in any normal distribution, that would be 95.5% of the cases, right?
Okay. Plus minus 2. बुझिन.
Plus or minus 2, 95.5%. But you know what? 95.5%. That 0.5% is kind of annoying, don't you think? Let's get rid of that. What I really want is just 95% of the cases exactly. Well, to get there, I go to plus or minus 2, and then I have to tuck it in a little bit from either side. Tuck it in how far? It turns out that tucking it into exactly plus or minus 1.96 gives me exactly 95% of the cases. How do you know that's true? Yeah, because I'm telling you it is. Just go with me on this. Plus or minus 1.96 gives you exactly 95% of the cases. Okay, so what percent of the cases in a z-score distribution fall between a z-score of +3 and -3? Well, that's easy. That would be 99.7% of the cases, just like any normal distribution. But you know what? 99.7. Once again, isn't that decimal, that 0.7, an annoying appendage? Yeah, let's get rid of that. Let's just focus on the 99% of the cases as a value. Well, once again, that means I go to plus or minus 3, and I have to tuck it in a little bit from either side. This time, I have to tuck it a little bit further to plus or minus 2.58 in order to get exactly 99% of the cases. So what? Well, we're now basically done, because we have all the values we need to complete our thought and indeed our computation for the confidence interval. It's really this simple. If I want to have 95% confidence, then I plug in to be the value of z 1.96. If I want to have 99% confidence, then I plug in my calculation as the value of z 2.58. That's it. Z is a simple binary switch. It's one of these two numbers depending on whether you want 95% confidence or 99% confidence. In my, here we go again, confidence interval, z is the confidence and the standard error is the interval. But wait, I'll make your life even easier. Because as you're whipping through, doing your calculation quickly on the exam, you're not going to use 1.96. That's likely too difficult to do a quick calculation. You're going to use what? You're going to use 2. It's what most people do. It's close enough. It'll get you close enough to get the proper answer. And you're not going to use, for 99%, 2.58. That's, again, too hard to work with. What are you going to use? Well, most people end up using 2.5. Please note 3 was too far. And please note 2.6 would frankly be a better number to use, but most people in their calculations default to 2.5, so you can feel free to do that as well. So for your exam and your calculation of confidence intervals, z is frankly just one of these two values. If the question says a 95% confidence interval, then z equals 2. If the question says a 99% confidence interval, then z equals 2.5. Easy. you now have everything you need to calculate your very own confidence interval of the mean. Hey, I have an idea. Let's do one together, don't you think? Get out something to write with. The margin of your notes is enough space. Let's actually calculate one together. Here's some data to use for that calculation. I got this data from a previous class, mean of 65%, standard deviation of 9%, and I got that information by talking to 9 students out of, frankly, a much mean of 65%, standard deviation of 9%, and I got that information by talking to 9 students out of, frankly, a much larger class. Using that information, please compute for me the 95% confidence interval for that estimate of the mean, the 95% confidence interval. Okay, well, I always like you to think about doing these questions in steps, in stages. So what do you do first? Well, the first thing you do is you write down the formula. And in case you forgot the formula, I've just put it on the screen before you. It's the mean plus or minus z times the quantity s divided by square root of n. Z times the standard error is how we're going to compute the confidence interval. You now have to take the values I gave you, plug it in the formula in order to derive the answer. So let's see, that's going to be 65 plus or minus, we said 95% confidence, that's a z-score of 2. And that's going to be then s is 9, and the square root of n is 9. So let's see, the square root of n, 9, is going to be 3. S at 9 divided by 3 is going to be 3. 2 z-score times 3 is going to be 6. And there you have the answer, which is 65 plus or minus 6. 65 plus or minus 6 is simply the 95% confidence interval for this estimate of the mean. What does that mean, 65 plus or minus 6? Simple. It means if I were to not merely stop with these 9 individuals, but I would in fact go and look at the entire class, getting everybody's scores, I would likely find the mean for the entire class is somewhere in the specified range of 71 to 59, somewhere in that simple range. Now, importantly, am I absolutely rock solid sure that the real mean for the class is somewhere in that range? Am I absolutely certain the real mean is somewhere between 71 and 59? The answer, of course, is absolutely not. I'm how sure? I'm 95% sure, because that's what I purchased with my z-score. I purchased 95% confidence. In short, if I were to do this repeated samples, 9 people in the class, and I would do this 100 times, I would find out that probably 5% of those 100 times, I would get a mean that's outside the specified range. Second issue, I said the real mean is somewhere in that range of 71 to 59, right? But come on, if I had to pick a single number, what's my best guess about what the mean is? If I had to pick a single number, my best guess is that the real mean is, and if you're thinking 65, please stop that now. The real mean is not most likely 65. The real mean is somewhere in that specified range, 71 to 59. Where? I don't know, and you don't either. All I know is this projection to reality. The mean is somewhere inside this range. And please note, this is not a bell-shaped probability distribution. This is a flat probability distribution. The actual mean is just as likely to be 71 as it is 65, as it is 59. It is not more likely to be in the center than on the extremes. Important idea. Please also understand what's happening as we're generating this confidence interval. We're using an essential trade-off. We started with a single number, very precise, from our data, 65, in which, if we're honest, we had 0% confidence that it was going to represent the mean of the class as a whole. And we traded that in for a 12-point range, not very precise, but in which we have 95% confidence. What we're doing in confidence intervals is essentially trading in precision for confidence. Trading in that single value, 65, 0 confidence, for this 12-point range, not very precise, but 95% confidence. In short, I give up knowing what the mean is from the data for knowing where the mean is, somewhere inside the confidence interval. Now, having made that point, let me just pause and have you think through what this confidence interval does not mean. I did not say 95% of the class falls inside this confidence interval. Let's say that again. I did not say 95% of the class is in this confidence interval, because to do that, thinking back, that would be the mean plus or minus 2 standard deviations, right? But I can't do that here. I can't. Why can't I take the mean plus or minus 2 standard deviations? That's easy, because I don't even know what the mean is. Well, sure I do. The mean is 65. No. That's just the mean of those 9 people. What I need to get the mean plus or minus 2 standard deviations is the actual mean of the class as a whole, which I do not have. My best estimate is a 12-point range, 71 to 59. So I can't take the mean plus or minus 2 standard deviations because I don't even know precisely what the mean is. Now, if you think this estimate, 12-point range, is rather broad, if you think estimating the mean only in that 12-point range is not really satisfying, well, the reason is I'm using only a very small amount of data to project to what reality is. And if I wanted a smaller interval, if I wanted a better guess about what the mean is, it should be obvious how I would get there. I increase the sample size. Take the same calculation, make the sample size, let's say 36, 49, 100. I'm trying to use numbers that have easy squares to them, of course. And as you do that and recalculate the confidence interval, as that sample size increases, you'll find your confidence interval decreasing rather dramatically. That should make not only, calculation sense, it should make logical sense, because as my sample size increases, my picture reality gets better, my confidence interval can therefore be narrower. And that's how we're going to calculate the confidence interval of the mean. Now, in addition to being able to calculate confidence intervals, I need you to be able to interpret confidence intervals. And now I want to turn our attention to interpreting confidence intervals as they might be presented to you on an exam question. We're going to, for a moment, step out of the realm of medicine into the realm of politics to try to get you to understand how these confidence intervals get used. Several years ago, there was a heated presidential campaign in which Barack Obama and John McCain were fighting it out for the presidency. Just prior to that election, I conducted a public opinion poll asking people who they preferred as their presidential candidate. People were given the options in my survey of expressing preference either for McCain or Obama. The results of my survey gave me the following. 44% of the people I talked to said they wanted McCain for president, whereas 48% of the people I talked to said they wanted Obama for president. Now, I got that information by doing a national telephone survey of 287 people across the United States. But that was it, just 287 people. And one other crucial piece of information for you. Over here on the left, it says plus or minus 3%. That plus or minus 3%, ladies and gentlemen, is an error of measurement. An error of measurement is used to mean a number of different things, but for our purposes, I want you to treat that as a 95% confidence interval. That plus or minus 3% is your 95% confidence interval. Good. That's the information. Here comes the question. With this data in hand, can you walk into Obama headquarters and tell him he's leading in the poll? In short, is Obama ahead, yes or no? And the answer is no, he's not. And here's why. We don't want to just stop with the numbers we have, 44%, 48%, because those are numbers generated just by talking to 287 people. And 287 people is not what it takes to elect a president. You have to anticipate from that sample what's the reality for the country as a whole, where our projection to reality is the 95% confidence interval, given here plus or minus 3%. So my best guess is that the support for McCain in reality could be as low as 41% or as high as 47%. And my best guess for Obama is that support could be as high as 51% or as low as 45%. The point, they could be the same. If they could be the same, I have no basis for declaring that they're different. Simple idea. When interpreting confidence intervals, in general, any overlap tells you there's no difference. And please understand the logic here. First, I estimate one reality for one group, McCain, somewhere in this range. Where? I don't know, but somewhere in the range. I then estimate a second reality for Obama, somewhere in this range. Where? I don't know, but somewhere in this range. But, well, if these two ranges don't overlap, then I can reach the logical conclusion the realities must be different, right? If the two realities do overlap, then I don't have that evidence, and I'm stuck with the conservative proposition they could be the same. Simple idea, simple key for your keychain, as I promised you. In general, any overlap means no difference, and since there is overlap here, I can't, with confidence, declare a difference. With those issues in mind, let's leave the realm of politics and return now to thinking about medicine. I want you to look at this particular graph with me, where we're showing you in graphic form the results of a research study where we're comparing 3 different antihypertensive medications called, all right, now very creatively, drug A, drug B, and drug C. The research design had us starting with 3 groups of hypertensive patients, all of whom had exactly the same blood pressures at the start of the study. So all we have to do to look at efficacy is plot their average blood pressures at the end of 6 months on medication. Blood pressure axis is the vertical, the 3 drugs are right along the horizontal, and, well, the little dots you see are the average blood pressures of each of the 3 groups relative to that vertical axis. The lines you see expending above and below those dots, that's the 95% confidence interval. All right, so that's the explanation, and now let's talk about what it is we're looking at. Given what's presented here, true or false? Drug A lowers blood pressure more than drug B. Well, if any overlap means no difference, that's of course false. You can see drug A and drug B, their intervals do overlap. Drug A lowers blood pressure more than drug C. Well, that one's true, because there is no overlap between the confidence intervals. And then, of course, B and C are not different at all, because C is subsumed within B. And so if you wanted a single sentence to summarize what's presented here, I would say A works better than C, and nothing else is different. Please notice that even though the difference in the means between A and B is greater than A and C, it's A and C that are different, not A and B. And why? Because reality is not those means, it's the 95% confidence interval that's presented here. Since they overlap, I have to say for B and A, there is no difference. Okay, now, we've been talking pretty exclusively about a 95% confidence interval. Let's shift for a moment. Let's shift to talk about a 99% confidence interval. First, is a 99% confidence interval going to be broader or narrower than a 95%? What do you think? Broader or narrower? Well, the answer, of course, is broader. First, when we're doing the calculation, that confidence interval, the mean, we're going to insert for the z-score 2.5 instead of 2. And that, just by brute mathematics, is going to give us a wider interval. Okay, but let's also try to think about this more intuitively. Suppose I were to run out of this room and go hide in one of the other classrooms in this building. Your job was to find me and bring me back to finish the lesson. Would you be more confident about finding me if you looked for me in 2 classrooms or in 4 classrooms? Well, the answer is, of course, you'd have more confidence looking in 4 classrooms. More area, more real estate gives you more confidence. A 99% interval will be broader than a 95%. Remember, we're giving a precision for confidence. So as we're gaining more confidence, we're going to be broader, that is, less precise. Let me now draw in for you the 99% confidence interval. That's the red I've just added to the slide. Okay, with that, please listen. At the 95% level, true or false, drug A works better than drug C. Well, that's true. It was true before. It's still true now. At the 99% level, drug A works better than drug C. Now that's false. We ever do more for you than you just did right there. You told me that your 95% sure they're different, but you're not 99% sure they're different. You made a decision and you quantified the certainty of your decision. This is how we use confidence intervals. And notice why. The researcher just didn't tell you, here's what I found. The researcher is showing you in the graph what they found and inviting you to look at the same data and see if you reach the same conclusion the researcher did. The reason why you're supposed to know about these confidence intervals is literally so you don't have to take somebody else's word for it. You can use your own thought, your own native intelligence, and see if you reach the same conclusion. Now, that's how we interpret confidence intervals of the mean when they're shown graphically or otherwise in research. I'm going to conclude this section about confidence intervals by talking about confidence intervals for interpreting relative risk. If you look at this table, you see we have presented for you in columns a set of relative risks, the presented set of 95% confidence intervals, and then some information about interpreting what it is you might be seeing here. I'm going to focus you, so let's focus just on the top row for a moment. You're presented with the relative risk, which is 1.77, and a simple question should come to mind. Is that 1.77 statistically significant? Well, you can't answer by looking at the number 1.77. You don't really have any information there. Instead, shift your attention where you always should to the reality, which is the confidence interval. The confidence interval in the parentheses, which is how it'll be presented on an exam question, ranges from a possible 1.22 to a possible 2.45. Please note that line is a dash, not a minus sign. Think about a number line that's being presented to you from a possible low of 1.22 to a possible high of 2.45. And the question is that indicative of statistical significance? And the answer is yes, it is.
Yes.
Now the reason why we know that is not because 1.77 fits.
Lo, chi hai? Se non lo niente. Không người cầm lại thôi đi. Để chúng nó làm sao thế? a bed break. Right. I'm feeling good now. See you in the हजुर क्यामेरा छु है साथीहरू setting webcam ke fine जस्तो भयो होस् अब पछि it's good I can put peacefully dun, 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 dun. Okay. 16 minutes to go. Dun, 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 dun. That's fine. Fine now. Okay.
It's inside that interval. It always will. Whether significant or not, it will always be inside the interval. Why? Because that's the interval around that relative risk calculation. The crucial number is not 1.77. The crucial number is down at the bottom over on the right. It's the number 1.0. And the question is, does the number 1.0 fit inside that specified range? As you can see,
बाबाको फोन थियो पढाउँ है त अब लेट्स रिड अगेन हैन नाउ आई एम फाइन आई थिङ्क हैन अहिले चाहिँ आई एम गुड I'm streaming right now. Nobody is watching me. हेर्नु पर्ने केटाहरू हेर्नु पर्यो नि पढ्ने भनेको डिस्टर्ब भइरहेछ खालि data other statistics there's no worries in it. Comparatively there are running stats. Finally statistics. Nice. Good. 300, 400, 500, 600 last 11 3 दिनमा oh nice. I'm doing good, you know, but सिक्सौँ होला nice. So Pinter's pathway, so Pinter's prospect pathway. So you bought I can do this way. Different thing, so it's process next encephalopathy. किन काटेँ मैले आँख बन्द भएको त्यही त काटेछन् बन्द भइरहेछ But I would no. procrastination. Procrastination.
Hi everyone, and welcome to our module on basic statistics. Let's suppose we randomly selected some healthy subjects and measured their blood glucose levels. We would get a collection of readings kind of like what I've shown on the screen here. There'd be a few people with low numbers like 85, and there'd be a couple of people with higher numbers, like there are some 112s in here, and then there'd be a lot of people in the middle. And if we plotted the blood glucose level on the x-axis and the number of subjects that had each level of blood glucose on the y-axis, we would get something that looks like this. There'd be some number in the middle here that was very common. A lot of people had this number in the middle. And as you went above it this way or below it that way, you would find less and less subjects had each measurement until you got down to some number that nobody had on either side. And it turns out a lot of things in nature have a distribution like this. We call this a normal or a Gaussian distribution. And it's clustered around some central number, and then it tapers out evenly as you go away from that central number, either higher or lower. And many things are like this. For example, if we looked at height of people, we could find a distribution like this. If we looked at weight, if we looked at the number of days people stay in the hospital for treatment for pneumonia, we might find a cluster around some central number of days, and then tapering out as you go above. Or below that. So many things in nature have this distribution, and therefore we spend a lot of time talking about how to characterize it in statistics. So the first characterization of that normal distribution I want to talk about are measures of central tendency. So you notice that the curve looked something like this, and it tended to collect around a central number, and we call that a central tendency. This is the center of a normal distribution. And there are three ways to characterize that central tendency of the distribution. The first is the mean, which is the average of all the numbers. The second is the median, which is the middle number of the data set when they're all lined up in order. And the third is the mode. It's the most commonly found number. And we'll talk about all three of these now. So just to keep this simple, instead of all those blood glucose levels, let's imagine that we had 6 recordings of systolic blood pressure. And they were 90, 80, 80, 100, 110, and 120. Well, the mean would be the sum of all 6 of those numbers divided by 6. So that's very easy to get. You've probably done this many times when you average things out. And that would be 96.7, this data set. The mode is the number that comes up most frequently. And in this data set, there are 2 examples of the number 80. So the mode would be 80. The median is the middle of the data set. And the way we determine the median is a little bit different depending on whether we have an odd number or even number of data elements. If we have an odd number of data elements, like suppose we just had 3, 80, 90, and 110, then the middle number is the median, and that would be 90. If we have an even number of data elements, let's suppose we had 80, 90, 110, and 120, then the median is going to be halfway between the middle 2 numbers, so it's going to be 100. So just remember that the median is a little bit tricky to measure. It's different from the other 2, and it depends on whether there's an odd or even number of data elements. And very importantly, you have to put all the data in order to find the median. First thing you have to do is start with the lowest number and work your way up to the highest number. Once you have them laid out, you can figure out the median value. So let's get back to this chart of blood glucose levels on the x-axis and the number of subjects with each recording on the y-axis. And let's figure out where the mean, median, and mode are for this distribution. Now, I haven't given you any numbers down here on the x-axis or on the y, but we can still figure out where the mean, median, and mode are just based on the shape. So the mode is very simple. It's always the highest point. Remember, the mode is the number that occurs most commonly, and we have number of subjects over here on the y-axis. So that's the number of times that recording occurs. So whatever this blood glucose level is the most common, and that's why it's the highest point on the curve. If the data are evenly distributed, like in this example here, where there's an even number of measurements on the left side and the right side of the mode, then the mean and median are equal to the mode. So anytime you see a nice, normal, even distribution like this, the mean, median, and mode are always at the top, right in the middle. Now, data sets aren't always evenly distributed. Sometimes they are what we call skewed, and data sets can have either a positive or negative skew. And the way to keep straight what's a negative skew and what's a positive is to look for the tail. So the tail of this data set is pointing in this direction, and that's towards the negative numbers over here. So when the tail points that way, it's called negatively skewed. And the way you figure out the mode, median, and mean in a negatively skewed data set is as follows. First of all, remember that the mode is always the highest point, so that's the easiest thing to find. Next, remember that the mean is always furthest away from the mode towards the tail, and then the median occurs in the middle. And these rules will still hold up when the data are positively skewed. So here's an example of a positively skewed data set, and you can see that the tail is pointing in this direction. It's pointing away from the negative numbers over here. It's pointing towards the really highly positive numbers over here. So once again, the mode is the highest point. That's always easy to find. The mean is always the furthest away from the mode, and then the median is in the middle right here. So a couple of key points to remember on these measures of central tendency. If the distribution is equal, if it's normally distributed, then the mean, mode, and median are all equal to one another. Remember that the mode is always at the peak. And then in skewed data sets, remember that the mean is furthest away from the mode toward the tail and the median is in the middle. And then a final point, and something that's very high yield to know for your exams, is that the mode is the least likely to be affected by outliers. When you add an outlier, it means you add one measurement that's very far away from all the others. This will have a slight effect on the mean and the median, but it's only going to affect the mode if it changes the most common number, and it's very unlikely that an outlier is going to change the most common number. That's why it's called an outlier, because it lies out and away from all the other numbers. So it's very unlikely that it's going to affect the mode. So the mode tends to stay in place when you add some unusual measurements to a data set. The mean and median are slightly affected by adding one outlier. So now I'm going to switch gears from talking about measures of central tendency and talk about measures of dispersion. Let's look at these two data sets charted on this slide. They both have a mean, median, and mode equal to 10. Their measures of central tendency are identical, but you can tell from looking at them that they're very different data sets. And what's different about these two data sets are the measures of dispersion that characterize them. So there are many different measures of dispersion that people use, but the one that you're most commonly going to see is the standard deviation. You may also see variance or standard error of the mean. Sometimes you will see z-scores, and sometimes you'll see confidence intervals. And we'll go over all 5 of these measures in the next few slides. So let's talk about standard deviation first. So standard deviation is represented by the symbol sigma right here, and this is the equation for standard deviation. Now, you're very unlikely to be asked to calculate a standard deviation on step 1 of the boards, but you do need to know how to interpret standard deviations. So let me show you how you get the number, and then we'll talk about how you use it. So first, let's talk about the elements of this equation right here for standard deviation. X minus X mean is the difference between each data point and the mean, and the sum of all the X minus X means is the sum of all the differences. So you're adding up how far away each data point is from the mean. Then you're going to square those differences, and then you're going to divide by the number of samples minus 1, and then you're going to take that entire thing and take the square root of it right here. So let me show you how you would do this for 2 different data sets. So we've got group 1 over here represented by these numbers right here, and the mean of all those numbers is 10. And then we've got group 2 over here represented by these numbers. So the first thing that we're going to do is determine the difference from the mean of 10 for each number. So 9, for example, is -1 from that mean, and 12, for example, is +2 away from that mean. And we're going to do the same thing over here. Represent the difference of each data point from the mean. Next thing we do is square all those numbers. So this is going to eliminate all the negative numbers and give us only positive numbers, and then we add them up. So for group 1, they add up to 11 because most of the data points in group 1 are close to the mean. In group 2, they add up to 96 because the data points in group 2 are further away from the mean. And now we're going to plug it into this equation up here in the top right, and we're going to take that summed value, divide by the number of samples minus 1, which is 7 in both groups, and then take the square root of it. And what we see is that the standard deviation for group 1 is 1.24, and the standard deviation for group 2 is 3.7. This means that group 1 is much more tightly oriented around that mean compared to group 2, which is much more spread out. Even though they have the same mean, the data are more dispersed in group 2, and that's why you have a larger standard deviation in group 2. So one of the things you definitely need to know for step one is how much of the data set you capture if you go one or more standard deviations away from the mean. So let's look at this data set right here, which has a mean right at this point I'm drawing here. If we go +1 standard deviation in this direction and -1 standard deviation in that direction, we will capture 68% of the data points within that range. If we go +2 standard deviations and -2 standard deviations, we will capture 95% of the data points. And finally, if we go +3 and -3, we will capture 99.7, virtually all of the data points within that range. So let's go back to those two curves I showed you before. They both have the same mean, median, and mode, but this one on the right is much more dispersed than the one on the left. Well, the rules still hold that if you go ±1 standard deviation on the left, you capture 68% of the data set. Same thing on the right. It's just that ±1 standard deviation represents more distance on the x-axis over here on the right than it does on the left. And then the same is true for the 95% intervals and the 99.7% intervals. So let me give you an example of how this kind of information might show up on an exam. Imagine that a test is administered to 200 medical students. The mean score is 80 with a standard deviation of 5. The test scores are normally distributed. How many students scored greater than 90 on the test? Well, the first thing we need to figure out is how far away from the mean 90 is. And 90 is 2 standard deviations away from the mean. The standard deviation is 5. 90 is 10 points away from that, so that's 2 standard deviations. So we know that ±2 standard deviations is 95% of the data. I've shown that down here on a picture. What you need to realize, though, is that means 5% of the data are outside this range, and that 5% is split up so that 2.5% is higher than this range and 2.5% is below this range. So this means that 2.5% of students scored above 90. That's in this top portion here, right there. And 2.5% of 200 is 5 students. And this is a type of question that often comes up on statistic exams or even in step 1. They will give you a data set and ask you to identify how many patients are in some range based on the number of standard deviations away from the mean. Most scientific literature you read will report a standard deviation, but once in a while you'll see a study that reports a variance. So remember that the standard deviation sigma is equal to the square root of all this stuff in here. Well, the variance is sigma squared, so you take away the square root, it's just the stuff under the square root sign. So sometimes this is reported instead, and it's just a different measure from standard deviation, but represent similar things. Those rules about 68% and 95% and all that don't apply to the variance. Those are only for the standard deviation. Next dispersion measure I'm going to talk about is called the standard error of the mean. And this represents how precisely we know the true population mean. In statistics, we often take a small sample and use its characteristics to estimate the characteristics of a larger population. For example, we might measure 10 systolic blood pressure readings and take the mean value and hope that that represents the mean value of a larger population of 10,000 people. The standard error of the mean gives a representation of how close we are to that true population mean. The standard error of the mean is equal to the standard deviation of our sample set divided by the square root of the number of samples. What this means is that the more samples we take, the less standard error of the mean is, the closer we are to the true mean. And this should make sense to you. If I take 10 blood pressure readings and use those to estimate the characteristics of 10,000 people, I could be way off. On the other hand, if I take 1,000 blood pressure readings and use those to estimate the characteristics of 10,000, I am probably closer to the true mean, and that's why the standard error of the mean gets lower the more samples you have. If you have a big standard deviation in your sample data set, this means you're going to have a big standard error of the mean. You're going to need a lot of samples in that case to make the standard error of the mean small. That's because the standard deviation is on top here. So if that's a big number, you have a lot of error. And the only way to cancel that out is to have lots of samples down in the denominator. A small standard deviation in your sample data set means a small standard error of the mean, and you don't need quite as many samples to still get a result with a low standard error of the mean. The next dispersion measure is the z-score, and the z-score is very simple. It's equal to the number of standard deviations you are away from the mean. So if a sample has a z-score of 0, that sample is equal to the mean. If the sample has a z-score of +1, it's 1 standard deviation above the mean, and if it has a z-score of -1, it's 1 standard deviation below the mean. So all these dotted lines here on this chart down at the bottom, which represent standard deviations away from the mean, can also be changed into z-scores by just writing -1 or +1. So just to make this very clear, in case you're ever asked to calculate it, suppose a group of students had a test grade average or mean of 79 and the standard deviation was 5. If your score on the test was 89, then your z-score would be 89 minus 79, which is 10 divided by 5, or +2. You would be 2 standard deviations away from the mean, and therefore your z-score is +2. The final measure of dispersion I want to discuss are the confidence intervals. So when you read the scientific literature, you will see most mean values reported with something called 95% confidence intervals. For example, a study of diabetic patients might report that the mean blood glucose level was 120 plus or minus 5. That plus or minus 5 is the 95% confidence intervals. And the authors are saying that this is the range in which 95% of repeated measurements would be expected to fall. The authors are saying that if you took our study of diabetic patients and repeated it, we believe that you would get a mean value of blood glucose that is similar to ours within plus or minus 5 of the mean that we got. So these confidence intervals are really for estimating population means from a sample data set. When the authors report their findings on a group of, say, 10 or 100 diabetics, they're trying to give you an estimate of what the mean would be like in the entire population of similar diabetics. So just to make this clear, suppose we take 10 samples of a population in the world that's represented by 1 million people. The mean of our 10 samples is X. How sure are we that the mean of the 1 million people is also X? The confidence intervals are what help us answer this question. So this is the equation for the 95% confidence interval down here on the bottom of the screen. It's equal to the mean value plus or minus 1.96 times the standard error of the mean. And let me show you how you would calculate that for a sample data set. So suppose we have a group of measurements and the mean value is 10, and the standard deviation is 4, and the number of measurements is 16. Well, recall from a few slides ago that the standard error of the mean is equal to the standard deviation 4 divided by the square root of the number of samples. So that would be the square root of 16. Well, the square root of 16 is 4, so this would be 4 divided by 4, and the standard error of the mean, therefore, is 1. This means our confidence interval is 10 plus or minus 1.96 times 1, and 1.96 times 1 is basically 2, so our confidence intervals are 10 plus or minus 2. So what we are saying is that we believe, based on this data set here, that 95% of repeated means would fall between 8 or 12. That's 10 plus or minus 2. And sometimes this is stated as the upper confidence limit being 12 and the lower confidence limit being 8. Now, it's very important that you don't confuse the 95% confidence interval with the standard deviation. Remember that I said that plus or minus 2 standard deviations includes 95% of a data set. That's completely different from the confidence intervals. The standard deviation is for a given group of data points. So suppose we have 10 samples. These 10 samples have a mean and a standard deviation. And 95% of these samples are going to fall between the mean plus or minus 2 standard deviations. This is purely a descriptive characteristic of the data set and all the samples. The confidence intervals, on the other hand, do not describe the sample set at all. These are an inferred value of where we think the true mean lies for a population. The confidence intervals help us tell readers of our clinical data how close we think our data set represents the population outside of our experiment. So when you see the number 95% in a question stem, don't get confused. Read the question very carefully. What are they asking for? If they say, what is the range in which 95% of the measurements in a data set fall, then they're looking for the mean plus or minus 2 standard deviations. On the other hand, if they say, what is the 95% confidence interval of the mean, then they are looking for the mean plus or minus 1.96 times Hi everyone, welcome to our module on hypothesis testing. So let's imagine that a
उज्जवल तिमी कहाँ हेरेर हो कि गयो उज्जवल हेलो उज्जवल कस्तो कम हेरिरहेको छ यार होइन
Cardiologist discovers a protein level that may be elevated in myocardial infarction patients, and he calls this protein MI-zyme, and he wants to use it to detect heart attacks among patients in the ER. So in order to see whether or not this might be useful for detecting heart attacks, he samples levels of MI-zyme among 100 normal subjects and also among 100 subjects with a myocardial infarction. The mean level in normal subjects is 1 milligram per deciliter, and the mean level in myocardial infarction patients is 10 milligrams per deciliter. So the question is, can this protein level, can this enzyme level test be used to detect myocardial infarction in the general population based on these two samples he drew up here? So another way to think about this question is, does the mean value of MI-zyme in normal subjects truly differ from the mean value in myocardial infarction patients? Or was the difference in our little experiment simply due to chance? There was definitely a difference in the mean between the 100 normal patients and the 100 heart attack patients, but maybe we just got lucky, and if we repeated it, we would not get that difference in means. So whether or not this difference is real or due to chance depends on three important factors: the difference between the mean values between the normal and MI patients, the scatter of the data points, and the number of subjects tested. And in the next few slides, I'm going to go through this to help you understand how we use hypothesis testing to determine whether differences between means are true or due to chance. So let's talk about the scatter of the data first. So let's imagine we plotted the MI-zyme level on the x-axis here, and on the y-axis we put the number of samples that were estimated at a particular level. So all the normal patients are represented by black dots, and most of the normal patients had levels way down over here around 1. Their mean is right here at 1, and the data are sort of scattered around that mean. All the MI patients had mean values that were much higher. Remember, it was 10. They're represented by these red dots, and so their mean is right here, and they're scattered about the mean. Well, it's very likely that these two differences are real because the scatter of the data in the two groups is very far apart from one another. In other words, the means are very far apart relative to the scatter in the data. It's pretty unlikely that the MI patients have the same mean level as the normal patients and that we just got lucky and pulled all these samples over here out for the MI patients. Because of how far apart these two groups are and how tightly the data points are collected around the means, it's very likely that this is a real difference. On the other hand, let's suppose the data looked something like this. Well, now we've got a lot more scatter. So even though the normal patients have a mean value that's far away from the mean value of the MI patients, there's a lot of scatter, and this data overlaps a lot. So now we begin to wonder, with this much scatter in the data and this much overlap, maybe the differences between the two groups were due to chance. And maybe if we collected more samples, we'd find that the means really aren't different. So the key point here, and what I'm trying to show you pictorially, is that the scatter of the data points influences the likelihood that there is a true difference between means. What statisticians do is apply numbers to the scatter of the data and use those numbers to estimate the likelihood that the difference between these two means is real and not due to chance. Another factor that influences the likelihood that the difference in the two means is real is the number of samples. So let's look here at this picture on the screen. The normal patients and the MI patients do have some overlap of data, but we have a lot of samples, and you can see that there's a high density of samples of normal patients way over here at this mean, and a high density of the red MI patients way over here at this mean. So these two means are more likely to be truly different because we've got a lot of samples, and they're really clustering far apart away from one another. So the key point here is the number of data points also influences the likelihood that there's a true difference between means. And we can be more confident when we detect a difference when we use a lot of samples. All hypotheses will reach this is similar, although it's different from the p-value. Hi everybody, and welcome to our module on neuroembryology. A few weeks after the egg gets fertilized, the developing embryo forms into layers that go on to form all the parts of the body that you know, and these are called the germ layers. So the mesoderm layer in the fetus goes on to form the cardiovascular system and things like muscles and bones. The endoderm layer goes on to form liver and lungs and the GI tract. But what we're going to talk about today mostly is the ectoderm, and this is what forms most of the central nervous system. So there's a surface portion of this ectoderm, and that forms things like the anterior pituitary, the lens, and the cornea. There's a neural tube, which is a very important structure we'll talk about in a minute, that forms the brain and the spinal cord. It also forms the posterior pituitary and the retina. The anterior and posterior pituitary have different embryonic origins, and that's why they have different functions in the adult. And then finally there's a portion called the neural crest, which forms the autonomic and sensory nerves, and it goes on to form the skull. So the neural tube is one of the most important embryonic structures, not only because it goes on to develop so much of the nervous system, but also because of failures in neural tube development are some of the most common neuroembryological abnormalities in babies. So to form the neurotube, which will go on to form the neural system, the whole process starts with something called the notochord, which is an embryonic structure. And it secretes signaling molecules that drive this process. And one of the signaling molecules has this very unique name, the Sonic the Hedgehog protein. There's a funny story behind this. There were a number of proteins at the time that looked like hedgehogs, and they had different hedgehog names. And the researcher who discovered this one, who ultimately went on to win the Nobel Prize, well, his kids were playing Sonic the Hedgehog all the time at home on a video game, so he named it Sonic the Hedgehog. So in any event, these signaling molecules induce the overlying ectoderm to convert and become what's called neuroectoderm. The neuroectoderm then becomes the neural plate, and the neural plate folds into the neural tube. It also goes on to form something called neural crest cells. And importantly, all this occurs around days 17 to 21, and at this point, most women don't even know they're pregnant. About half of all pregnancies are unplanned. So women can already have a problem in the fetus before they're even aware they're pregnant, and we'll talk about this later, but that's why women of childbearing age are encouraged to take folate if they think they might get pregnant at all. And incidentally, the notochord in the adult is what goes on to form the nucleus pulposus, which is the intervertebral discs in the spinal cord. So here's a picture to help make all this neural tube development make a little more sense. So here's the ectoderm here, and this is the notochord right here. And it's going to trigger this overlying ectoderm to become things like the neural crest cells and the neural plate. And the neural plate is going to involute to form the neural fold, and then the neural fold will close to form the neural tube. Now, if the neural fold doesn't close and part of it stays open, that's how you get spina bifida, which we'll talk about in a few slides. And this is just a picture of the spinal column in the adult. So here's the spinal cord in the middle, and these are the vertebral bones, and right here is the nucleus pulposus. It's the intervertebral disc, and that's the remnant in the adult of what was the notochord in the developing fetus. So the neural tube has a series of bulges and swellings that go on to develop the structures in the adult, and you need to know what they are. So initially, it forms three primary vesicles, which are really just bulges of the tube, and the first one is called the forebrain. It's also called the prosencephalon. The second one is called the midbrain or the mesencephalon, and this will persist into the adult and be the midbrain that you know from studying brainstem anatomy. And then finally there's the hindbrain, which is also called the rhombencephalon. These three primary vesicles form 5 secondary vesicles, which are called the telencephalon, the diencephalon, the mesencephalon, the metaencephalon, and the myelencephalon. So this is easier to understand if you look at a picture. So over here on the left side of the screen are the 3 primary vesicles. Those are the prosencephalon, mesencephalon, and rhombencephalon, and they form the secondary vesicles, which are all listed right here in the middle of the screen. And those go on to form the structures that you know in the adult. So the telencephalon forms the cerebral cortex and cerebrum. The diencephalon forms important structures like the eye, the thalamus, the hypothalamus. The mesencephalon will stay the mesencephalon and be the midbrain that you know from studying the brainstem in the adult. The metencephalon forms the pons and cerebellum, and finally the myelencephalon forms the medulla oblongata. And the primary brain vesicles are present at about 3 to 4 weeks in the embryo, and it's about 5 weeks when you see the secondary ones form. So the clinical relevance of all this embryology I've been telling you about is there are congenital defects of the nervous system that happen when baby's nervous system doesn't form properly. So the most important ones are the neural tube defects. The first of these is spina bifida, and this is when the caudal or bottom end of the neural tube doesn't close. The next one is anencephaly, and this is when the head or rostral end doesn't close. There's also a neural tube defect called an encephalocele. There are also cephalic disorders we'll talk about, like holoprosencephaly, and then finally there are disorders of the posterior fossa, which are basically cerebellum problems, and these are the Kari malformations and the Dandy-Walker lesion. So we'll go through. all of these in this module now. So neural tube defects happen when the neuropores fail to close in the fourth week. So what are the neuropores? Those are openings of the neural tube. And remember I showed you that it starts with a neural fold and then it has to close into a tube. And if it doesn't close and one of those neuropores stays open, you will get a neural tube defect. If you have the rostral neuropore fail to close, you get a defect at the head. Rostral means towards the head. And if the caudal neuropore doesn't close, that means you get an opening down towards the tail. So spina bifida is when the caudal neuropore fails to close posteriorly and you don't get bones growing around the spinal cord and meninges. We'll talk more about that in a minute. Anencephaly literally means without head, and that's when the rostral neuropore fails to close anteriorly and you basically get absence of major portions of the brain and skull, and this is not compatible with life. We'll talk about this in a minute. There are some well-known risks for neural tube defects that you should know about, and one of the biggest is decreased folic acid intake in mothers. And this is why women who are pregnant or may be pregnant are advised to take folic acid. And remember, the neural tube defects occur in the first few weeks before most women even know they've missed a period and they are pregnant. So women of childbearing age are advised to take folate if they think they might become pregnant. Type 1 diabetes is a risk, obesity is a risk, and then there are two anticonvulsants, valproic acid and carbamazepine. I talk about these in the seizure module, but they are well-described risk factors for neural tube defects. There are three forms of spina bifida, all caused by failure of the caudal neuropore to close appropriately. So let's talk about the three forms now. The first type is called spina bifida occulta. In this condition, the bones around the spinal canal fail to fuse normally, as shown in this picture. However, the meninges and the spinal cord are normally positioned. Usually the only abnormality you can see on physical exam in this condition is an abnormal tuft of hair or a dimple over the spinal canal. That's why it's called occulta, because the spinal problem is hidden. The next type is called a meningocele. In this condition, the meninges bulge out from the back of the baby. However, the spinal cord remains in the spinal canal. And then the worst type is called a myelomeningocele. In this condition, both the spinal cord and the meninges are bulging out from the back of the baby. This type of abnormality is almost always associated with a Chiari malformation, which is an abnormality of the cerebellum. Here's a drawing of the spinal cord in cross section just to make this more clear. So on the left side is a normal spinal cord and vertebral column. In spina bifida occulta, the only issue is a gap in the bones, but nothing is protruding through that gap. Remember, there's usually that abnormal tuft of hair, or sometimes a bump or hemangioma is present. In a meningocele, the meninges are bulging out through the gap in the bones. And then finally, in a myelomeningocele, both the spinal cord and the meninges are bulging out through that gap in the bones. And this is the type that is almost always associated with a Chiari malformation. So you should know that spina bifida defects can usually be detected in utero. This is part of why women undergo prenatal screening and prenatal ultrasounds. And in fact, there are surgeries that can repair the defect, and some of them can even be done in utero, although others are done right after birth. The problem is that unfortunately a lot of children, even if they get the defect repaired, are left with permanent neurologic deficits. So you've probably seen children in wheelchairs, and what they had was spina bifida when they were born, and even though it got surgically repaired, they've never fully recovered the ability to walk. Some of them are paralyzed, some of them have permanent bowel and bladder problems. And this is a fetal ultrasound of a baby with spina bifida, and you can see the defect in the back of the spine. So anencephaly is another neural tube defect, but in this case the portion of the neural tube that fails to close is up near the head, and the forebrain and brainstem get exposed in utero, and when they're exposed they don't develop normally. This is not compatible with life. The baby will be stillborn or die shortly after birth, and you can detect this on ultrasound. Babies will have what's called an open calvaria. The calvaria is basically the formation of the skull, but it will be open, and the fetus has a frog-like appearance, and that's a classic description for board questions. Also important to know is that the mother will have polyhydramnios. So polyhydramnios means excess amniotic fluid. And the way amniotic fluid is produced is it's the baby's urine, and then the baby swallows it to take it back into the body. But babies with anencephaly can't swallow the amniotic fluid, so the mother is going to develop polyhydramnios. And then one other type of neural tube defect is called an encephalocele. Down here on the right there's a picture of a baby with one of these. This is where brain or meninges herniate through a skull defect. It's the least common type of neural tube defect, and the most common site for this to occur is the occipital bone. So alpha-fetoprotein is a protein synthesized by the baby in utero, and when that level of this protein is high, it suggests a neural tube defect. It's a fetal-specific globulin. It's made by the fetal yolk sac and some of the fetal organs. We actually don't know exactly what the purpose of this protein is in the developing baby, but we do know it's excreted by the fetal kidneys, and at about 16 to 18 weeks you can measure the AFP level in the mom's bloodstream, so you can draw blood from the mother and detect alpha-fetoprotein. If the level is high in the mother's bloodstream, this may indicate a neural tube defect. Now, interpreting alpha-fetoprotein levels is complex, and a high level doesn't necessarily guarantee a neural tube defect, but it is suggested. When the level of AFP is high, mothers are usually recommended to get follow-up tests, and often this is an amniocentesis, where a needle is inserted and some amniotic fluid is drawn out for testing. If the level of amniotic fluid AFP is high, that strongly suggests neural tube defect, and they will also check something called the amniotic fluid acetylcholinesterase level. If both of these are high, it strongly suggests a neural tube defect. When you do OB rotations, you will see women who are pregnant come in for what's called prenatal screening, and one of the things they are screening for are neural tube defects in the baby. Partly they'll do this by ultrasound. As I showed you before, you can see some neural tube defects by fetal ultrasound, and they will also check the maternal blood level of alpha-fetoprotein. Now, they are also going to screen for Down syndrome at the same time. There are markers of Down syndrome by fetal ultrasound. One of the classic ones is for the nuchal area at the back of the neck to become translucent, meaning it's clear and dark on ultrasound. And they will also send serum markers in the mom's blood for Down syndrome. Usually what they send is what's called the triple screen. So they test the mother's blood for AFP, estradiol, and HCG. AFP is high in neural tube defects, like I said, and it's actually low in Down syndrome. And then levels of estradiol and HCG are abnormal in the mother's bloodstream when there's Down syndrome. So this is what prenatal screening is all about, and it's looking for neural tube defects in addition to Downs and other problems. Okay, now we're going to talk about holoprosencephaly, and this is a cephalic malformation. It's failure of the prosencephalon to cleave. I'll show you a picture of that in a minute, but remember the prosencephalon was one of those developing areas of the neural tube, and the left and right hemispheres of the brain, which as you know are supposed to be separate, do not separate. It usually happens during weeks 5 to 6. And it is a failure of signaling molecules, that sonic hedgehog protein. Again, is implicated, and this protein has so many effects. It's part of why the researchers who discovered it won the Nobel Prize. The key findings for babies who have holoprosencephaly, you can't see their brain and that's not separated, but when you look at the baby, you'll see facial abnormalities. The mild forms are cleft lip and palate. If it's severe, they may have just one eye. That's called cyclopia. And it's associated with some other chromosomal abnormalities like trisomy 13, trisomy 18, and it's also associated with the fetal alcohol syndrome. And so here on the left side of the screen is a normal prosencephalon, and it's separated into two parts like it's supposed to. But over here on the right is a holoprosencephaly prosencephalon, and the cerebral hemispheres are still stuck together, and the optic neuroectoderm did not separate. So when you look at the baby's face, if it's mild, you might just see a cleft lip, which is what that is right here. If it's severe, you can see cyclopia like this, where the baby has just one eye. Next, we're going to talk about the Chiari malformations, and these are all abnormalities of the cerebellum. That's the way I always remember it. They are a group of disorders numbered 1 through 4, but you only need to know numbers 1 and 2 because 3 and 4 are incredibly rare. And they all involve downward displacement of the cerebellum, and there's a picture of that down here. So the cerebellum has started to move downward through the foramen magnum, and there it can compress the brainstem, which is one of the problems in Chiari malformations. And it can also obstruct CSF flow and give hydrocephalus. And those are the two major issues that children with Chiari malformations have. So we'll talk about the Chiari 1 malformation first. This is where you have an abnormal shape of the cerebellar tonsils, and the tonsils are these small rounded structures at the bottom of the cerebellum. And the tonsils get displaced downward below the foramen magnum. Here's a picture of it over here on the right side of the screen. And it's very high yield to know that Chiari 1 malformations are associated with syringomyelia. We talk about syringomyelia in the spinal cord module, but this is a picture of it over here on the left side of the screen, and it's a cyst in the middle of the spinal cord, and it causes very specific symptoms. Because this is a smaller malformation than Chiari 2, patients often don't have symptoms until they get into adolescence or adulthood. The mean age when people get symptoms is 18 years. One of the first things they get is headaches, and this is because their meninges are being irritated by the malformation. They classically complain of something called a cough headache, where their headache is worse when they cough. They also get cerebellar dysfunction, so they can have ataxia, and they can have cranial nerve dysfunction because that herniated cerebellum can compress the brainstem and give you cranial nerve lesions. So a Chiari 2 malformation is also called an Arnold-Chiari malformation, and this is downward displacement of the cerebellar vermis and tonsils. It's much more of the cerebellum that's displaced. This usually causes a brainstem malformation. You can get something called a beaked brainstem on neuroimaging because the malformation is compressing the brainstem. And remember what I said before, these patients almost always have a spinal myelomeningocele. And because of that, this is usually detected prenatally because the myelomeningoceles can usually be seen in a fetal ultrasound. So the big problem with these malformations is that it blocks the aqueduct and gives hydrocephalus. And remember what I said, before there were shunts available in the 60s to lower the pressure in the head, most babies with this malformation died from hydrocephalus. Because of the myelomeningocele, there's usually paralysis below that defect. And just keep in mind that hydrocephalus in infants doesn't present the way it does in adults. So adults will come in complaining of a headache, but a baby can't complain of a headache. So what will you see if a baby has hydrocephalus? You'll see a large head circumference on growth curves. So when you do a pediatrics rotation, you always measure the circumference of the child's head and compare it to a growth curve. If it's too large, that may suggest hydrocephalus. Babies can have their anterior fontanelle distended. The fontanelle is the space below skull bones, and it seals in childhood, but it can be distended in babies. The sutures, which are the spaces between the skull bones, can be widely split. And there's a classic finding of a cracked pot sound. It's also called McEwen sound when you percuss the skull in babies with hydrocephalus. I don't think anyone does this anymore, and these problems are usually picked up in utero or right after birth, so the children never go on to get this sick. If they did walk in with an undiagnosed Chiari 2 malformation and hydrocephalus, these are some of the things you might see. So the last malformation we'll talk about is called the Dandy-Walker malformation, and this is a developmental anomaly of the fourth ventricle. It's also often detected by ultrasound in utero, and you get poor development of the cerebellum is the bottom line. Technically, it's hypoplasia or agenesis of the vermis. The cerebellar hemispheres, they look flattened when you image them, and they're separated from each other by something called a Dandy-Walker cyst. And you get cysts in the fourth ventricle which cause hydrocephalus. Hydrocephalus is the main problem in this abnormality. There are many, many associated symptoms and conditions, and this is really rare, and I don't think it's worth your time to remember them all. But suffice it to say that affected children will have hydrocephalus, delayed development, and they will have motor dysfunction because they are not crawling and walking normally. And this is a brain image of a patient with the Dandy-Walker malformation. And what you see is that the cerebellum is small, and there's a huge space in the back of the brain. And if you see that, that's a classic finding for Dandy-Walker malformation. And that concludes our module on. Hi everyone, and welcome to our module on delirium and dementia. So dementia and delirium are both conditions where people get confused, but they're distinctly different pathologically and in the way they present, and you need to be able to tell them apart. So dementia is a chronic confusion. It's usually a progressive, slowly progressive cognitive decline, and it's usually due to an irreversible underlying pathologic process. Delirium, on the other hand, is acute confusion. So you can get acutely delirious with a high fever, for example. It often has a waxing and waning pattern where people will be more oriented for a period of time and then more confused, and this will change over the course of hours. And delirium is usually due to some type of reversible cause, like the fever I mentioned. That delirium will get better when the fever goes away. So let's talk about delirium in a little more detail. And remember, this is an acute onset of confusion. So patients who are delirious can't focus and pay attention. Their thinking is very disorganized. They sometimes have hallucinations, often visual, and this is less common in dementia. And their sleep-wake cycle is disturbed. So a delirious person is often up and agitated at night and may be somnolent during the day. So delirium is usually secondary to another cause, often a medical condition or a drug. So infection can make people delirious. Drinking alcohol can make people delirious. Patients who are withdrawing from alcohol or opiates will be delirious. And then the most common cause, and something that you're definitely going to see on clinical rotations, is dementia patients who are in an unknown setting. So demented patients orient themselves by getting familiar with their surroundings. So when they're at home, they recognize where they are, and this keeps them calm and oriented. But if you take that demented patient out of their home and put them in an unfamiliar hospital surrounding, they will suddenly become delirious. So for example, a patient who has baseline dementia and develops pneumonia and gets hospitalized will often get delirious. It's because they're in an unknown setting and also because they have an infection. And this is the most common reason for altered mental status in the hospital. It's a demented patient who is now sick and out of their familiar surroundings. Normally we diagnose dementia and delirium clinically through patient's symptoms, but sometimes you can use a tool called an EEG, which is an electroencephalogram. And this is a picture here of a patient hooked up to an EEG machine. And it records voltage changes in the brain as are both conditions where people get confused, but they're distinct. Often as a cause, delirious. The most common cause in some delirious, their thinking is very disorganized. They sometimes have hallucinations.
time लाग्छ यार बिल्कुलै धेरै टाइम लाग्यो नो 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 कति बहुत टाइम भइसक्यो फर्स्ट सेकेन्ड त कहिले इसी का याद तो मैं लोगे याद नहीं हो रहा ड्राइवर में तो ये 2 मिनट लगा 2 मिनट्स फर्स्ट में पहला वीडियो मतलब फास्ट थी अरे 10 सेकंड का है ना Oh, I think I'm fine now, eh? Lo, मिल गया lo. Oh my god, के भएको? मैले बेसी बनाउनु यार. I'm sorry, रेकर्ड भइरहेछ रेकर्ड नगर्नु पर्ने. है? रेकर्ड भइरहेछ है. मेरो बिल्ला भयो नि त. बल्ल भएर. मैले अलि मिस्टेक गरेँ नि त. No worries. बल्ल भयो. सुन्नु है पढ्नलाई. अलि पढ्नु मन लागिरहेछ मलाई. टाइम भयो पनि. Let's go another session.
Hallucinations, often visual, and this is less common. Usually orient themselves how unknowns. They will suddenly become delirious. And this is the most common reason for altered mental status in the hospital. It's a demented patient who is now sick and out of their familiar surroundings. Normally we diagnose dementia and delirium clinically through patient's symptoms, but sometimes you can use a tool called an EEG, which is an electroencephalogram. And this is a picture here of a patient hooked up to an EEG machine. And it records voltage changes in the brain as nerve cells depolarize. It's very similar to the EKG for the heart. And just like the EKG for the heart, there are different leads to record different areas of brain cell activity. So there are frontal, parietal, and occipital leads on the patient's brain. And there are characteristic patterns for many different neurological conditions. Something that's important for you to know, especially for your boards, is that the EEG is going to be normal in patients who have dementia, but it is abnormal in patients with delirium. And over here on the right, I've shown you an EKG tracing. So if you're on one of your clinical rotations and a medical patient is delirious at night, how are you going to treat that? Well, the first thing you want to do is fix the underlying cause. So if
Wait. Okay. I do not want because I want to finish something.
If they're delirious because they're withdrawing or because they're infected, you need to treat that. If they're hypoxic, you have to fix their low oxygen levels. Patients who are in pain can become delirious, and if you treat the pain, they will get better. And patients that are dehydrated can also get delirious. So you want to take care of all these sort of routine things to make sure the patient's not delirious from some quick reversible cause. You want to put them in a calm, quiet environment, so noisy hospital wards are not helpful for delirious patients. And then finally, if they continue to be agitated and delirious and confused, we sometimes use drugs. And the most commonly used drug to treat delirium is haloperidol. It's often called vitamin H by house staff. So haloperidol is in a class of drugs called neuroleptics, and these are drugs that treat confusion and mania. The first one developed was chlorpromazine. So prior to the development of this drug in the 1950s, patients who had schizophrenia were often institutionalized and restrained and sometimes subjected to lobotomies to try and eliminate their agitated behavior. When chlorpromazine came along, this was the first drug that could actually calm patients with severe schizophrenia down, and it led to a lot of reduction in use of restraints, and it led to a lot of drug development, and subsequently some of these other drugs were developed, and now haloperidol is one of the main ones that we still use today. So the main effect of haloperidol and these neuroleptics is to block central nervous system dopamine receptors. Now they also block acetylcholine and alpha and histamine receptors, and we'll talk about this later, but this is responsible for a lot of the side effects. And drugs like this are used in schizophrenia and psychosis and mania, and then we use them in the hospital to treat acute delirium. So we break them down into the so-called high-potency agents and the low-potency agents. The high-potency agents are haloperidol, trifluoroperazine, and flufenazine, and these have many neurological side effects, and they also have something called extrapyramidal side effects, which we'll talk about in a minute. The other two agents, like thioridazine and chlorpromazine, we don't use that much anymore, but these have fewer of the neurological and extrapyramidal side effects. They have more of the non-neurological side effects, and we'll talk about those in a minute. So what do we mean when we say that a drug has an extrapyramidal side effect? Well, the pyramidal system is basically the corticospinal tract. This is your motor system of your body. It runs in the pyramids of the medulla. That's how it gets its name. And damage to this system leads to weakness. The extrapyramidal system is associated with the basal ganglia and its associated tracts, and it modifies movement. These are tracts like the rubrospinal tract and the tectospinal tract. They all modulate movement. And so when you have damage to the extrapyramidal system, you get movement disorders. It's not so much paralysis like with the pyramidal system, but it's difficulty coordinating movements, or it's movement that you don't want. So Haldol has a number of extrapyramidal side effects, and the exact mechanism of these side effects is not known. It's believed to be a response to dopamine blockade in the central nervous system. And there are 4 movement side effects, or extrapyramidal side effects of Haldol, that you should know about: dystonia, akathisia, bradykinesia, and tardive dyskinesia. And I've listed them here in the order late. That's an easy way to remember that, within hours or maybe days. It's an involuntary contraction of muscles. I think of it as a muscle spasm, or some people describe it as stiffness in the muscles. And you can treat it with an anticholinergic medication called benztropine. Akathisia is something that occurs after being on haloperidol for several days. It's basically restlessness, or some people describe it as an urge to move. It can be misdiagnosed as worsening agitation, and you can treat this by lowering the dose of haloperidol or using benzos, or sometimes people use the beta blocker propranolol.
Right. Psychiatry. Coordinate transference. Primes CKZ. CZD.
Bradykinesia occurs after you've been on haloperidol for several weeks, and it's basically Parkinsonism. It's drug-induced Parkinsonism, slow movements, difficulty initiating movements, and this also can be treated with benztropine. And then tardive dyskinesia is something that's rarely seen in the modern era, but it used to happen a long time ago when people took drugs like Haldol for years on end. And it's an irreversible condition where patients get chorea, which are those snake-like abnormal movements. They will smack their lips and grimace. And like I said, it's irreversible. Stopping the drug usually doesn't help. Once patients have developed tardive dyskinesia, they will usually have it for life. So for your boards, it's important to remember now, by mouth interval on the EKG. This is a very rare but very dangerous reaction to these drugs. And an easy way to remember it is that it's very similar to malignant hyperthermia, which is a rare reaction to halothane and succinylcholine. And in fact, it has the same treatment as that condition, which is dantrolene, a muscle relaxant. So NMS is a side effect that usually occurs 7 to 10 days after treatment with Haldol. So what happens to patients with NMS is they get fever and rigid muscles. And if you see fever and rigid muscles in a board question stem in a patient on a neuroleptic, this is the first thing you should think of. They also develop mental status changes. They get an encephalopathy. They get hypertensive and tachycardic from autonomic instability. Their CK levels will become very high, and this can cause myoglobinuria and acute renal failure from rhabdomyolysis. So what you want to watch is for fever, rigidity, and confusion after a dose of Haldol. The treatment is dantrolene, which is a muscle relaxant, and you can also use bromocriptine, which is a dopamine agonist. So now we're going to talk about dementia, which in contrast to, so the classic, it's usually irreversible, unlike delirium, which you can often make go away. Anyone who has Alzheimer's disease, you probably have seen all of these things. So aphasia is in what you're saying, motor tasks, so they can't do their job. So people with Alzheimer's can't function around the house. They can't do activities of daily living like cook for themselves and get to the bathroom. When the Alzheimer's gets severe, some patients can't chew, swallow, or walk. And then they also have agnosia. This is the inability to correctly interpret senses. So people who have severe dementia won't recognize their friends or even their family. A lot of times they can't interpret a full bladder, so they will urinate on themselves, and they can't interpret pain correctly, so they'll get agitated when they feel pain. Clinically, we assess patients with dementia using something called the mini mental status exam. So this is a series of questions you ask, and they get points for each correct answer. And more than 27 points out of 30 is considered normal. So just to give you some examples of some of the questions in the mini mental status exam, you check to see if they're oriented at time and place. You give them 3 objects and see if they can remember them and repeat them back to you. You will ask them to count from 100 backwards by sevens or to spell the word world backwards. You'll ask them to name an object you point out to them. This is testing for agnosia. You will ask them to repeat a phrase, and sometimes you'll ask them to draw an object that you show to them. And all these are parts of the mini mental status exam, and patients with dementia will have scores under 27 out of 30. So let's talk about the causes of dementia. Far and away the most common is Alzheimer's disease. This is about 60% of cases. After Alzheimer's, it's multi-infarct dementia, which is basically a series of small strokes that results in dementia. Third most common cause is Lewy body dementia, which we'll talk about in this module. After these 3, everything else is very, very rare. There's something called Pick's disease, which we'll talk about in a little bit, that can cause dementia. Normal pressure hydrocephalus can cause dementia. Creutzfeldt-Jakob disease, which we'll talk about later, can cause dementia. You can also get dementia from advanced HIV, certain vitamin deficiencies, and then from Wilson's disease as well. So Alzheimer's disease is the most common cause of dementia, and it is degeneration of the cortex. So contrast this with the basal ganglia that degenerates in movement disorders. When you get degeneration of the basal ganglia, you usually get unwanted movement like Parkinson's and Huntington's disease. When you get degeneration of the cortex, you get dementia. This is a generalized degeneration of the cortex, so it usually doesn't cause focal deficits. It causes a global loss in cognitive ability. The hallmark of this condition from a neurotransmitter perspective is loss of acetylcholine cortical activity. There's a deficiency of choline acetyltransferase in patients who have dementia, and this is very prominent in places where acetylcholine is important, like the basal nucleus of Meynert and the hippocampus. It's high yield for your boards to know a little bit about the Alzheimer's biochemistry. So there's a protein called amyloid precursor protein, which is normally found on neurons. And it usually gets broken down into an alpha degradation product that doesn't go on to cause any problems. But sometimes, for reasons we don't understand, it gets broken down into a beta product. And this beta breakdown product can form alpha-beta sheets of amyloid, which can build up in the brain and cause Alzheimer's. Now, a lot of research has gone into which genes put patients most at risk for Alzheimer's, and you should know that there is an epsilon 4 allele of the apolipoprotein E molecule that increases the likelihood that amyloid precursor protein will become the beta breakdown product and cause Alzheimer's disease. There's also an epsilon 2 allele of that same apolipoprotein E, which is protective. It makes it less likely that the beta breakdown product will form and that you will go on to develop Alzheimer's.
खाना मिल्छ कि मिल्दैन अब यो
Nice question. Does the disease commonly presents with body disease as in भएपछि यो कहीँ नेफ्रोटिक हो र एसेन्जियलमा हुन्छ हिमाचिलिया हिमाचिलिया भन्छ नेफ्रोटिक हो वाउ थाहा छैन मलाई चेक गरेँ मलाई बेल्जियस BIGER के हो बेल्जियर कहाँ छ के आयो है youngest fibers of थाहा छैन सुपर इन्डिजन TSST थाहा छैन मलाई primary care patient for physically examinations hyper extensive skin hyper extensive skin भनेको यो इलास्टिक हो सायद को आयो फेरि को बोलिरहेको वही हल्लानगर माथि साउन्ड आइरहेको छ साउन्ड आइरहेको छ माथि हेलो हेलो सुन्दैन होला फ्यानको रिप्लाई नदिएको दिइरहेको छु त मुला अब अनसब्सक्राइब गरिन्छ त्यसो नगर्नु न दोस्त हजुर नै हो बरु सेयर हान्नु साथीहरूलाई जबरजस्ती सब्सक्राइब गर्न लाउनु मलाई सबैको सपोर्ट चाहिन्छ सपोर्ट मी यस नै हो लामो होइन रहेछ दोस्त होइन रहेछ भिडियो म्युट छ र सुनेन भन्छ अहिले बोलिरहेको छु त म दोस्त सुनेनौ नमस्ते तर निश्चय गरिदिन्छु नमस्ते प्रकाशजी नमस्ते हजुरले सेयर गरिदिनुपर्छ है सेयर गरिदिनु के हेर्नु थाल्दियो भर्खर के हेर्नु थाल्दियो धन्यवाद 2000 साल glycoprotein किन अरे किन यो मिस्टेक भएछ एउटा यहाँ ठिकै छ डायग्नोस्टिक पनि गरेको छु होइन एलर डाङ्गस छ्या जोइन्ट स्किन होइन हाइपर एक्सटेन्सिभ स्किनहरू जोइन्ट छैन सो जोइन्ट भनेपछि मार्फान Galpost Kat Sebastian इसमें इक्विवेलेंट डिफरेंस है easy breathing cool 3A okay I'll put on a 4 bar दामी छ्या
So just a word about amyloid in general. These are proteins that are found in many different diseases, and they build up in the extracellular space. They all stain with Congo red, and they all have apple green birefringence when you look at them under polarized light. The disease process depends on where they are found. So you can get amyloid heart disease and amyloid kidney disease, but when amyloid builds up in the brain, that's when you get Alzheimer's disease. The most important risk factor for Alzheimer's is age. Alzheimer's is largely a disease of the elderly. Most cases are considered sporadic, meaning that they are not caused by a mutated gene that is passed through families. There are a couple of situations where patients can develop Alzheimer's at a younger age. One of the most important is the Down syndrome. As you may know, children born with Down syndrome have 3 copies of chromosome 21, and the APP gene is found on chromosome 21. Therefore, it should make sense to you that children born with Down syndrome can develop Alzheimer's and can develop it at an early age. In fact, most children born with Down syndrome will develop Alzheimer's by the time they reach their 40s. There are also rare familial forms of Alzheimer's. These are in contrast to the usual sporadic forms. These are passed down through families due to gene mutations, usually caused by a mutation of genes called presenilin genes. There are 2 of these, presenilin 1 and 2, and they've been found to be mutated in cases of familial Alzheimer's disease. Other risk factors include African American.
That's why
Race, African Americans are more likely than whites to develop Alzheimer's. If you have any family history, you're more likely to get the condition. Obesity is a risk factor, so is type 2 diabetes, but interestingly not type 1 diabetes. It appears you need to be resistant to insulin in order to be at increased risk. Hypertension and hyperlipidemia are established risk factors. And finally, traumatic brain injury is a very interesting risk factor. If you've ever had a brain injury and lost consciousness for more than 30 minutes, you are more likely to get Alzheimer's. Patients with Alzheimer's, and finally, traumatic brain injury is a very interesting risk factor. If you've ever had a brain injury and lost consciousness for more than 30 minutes, you are more likely to get Alzheimer's.
okay. Yeah. पापल्लाबाट गर्नु पऱ्यो भने त सिकिहाल्छ नि कसरी स्नो र कहाँ हुन्छ अझमा कुन पार्टमा म्याक्सिमम यो त क्याम्पस
Patients with Alzheimer's get atrophy of their cortex. So this means that the gyri of the brain narrow and the sulci widen. So let's look over here on the right. This is a patient with severe Alzheimer's disease. So these sulci, these spaces between the tufts of brain, get wider and the gyri get narrower as compared to somebody with a healthy brain. They also get what's called hydrocephalus ex vacuo. This means that the ventricles appear larger on CT and MRI imaging, and it's not that the ventricles are getting larger, it's that the cortex is getting smaller. Let's talk about the pathology of Alzheimer's disease. You can see beta amyloid plaques on microscopy, and this is an example of what one looks like here. And you also see characteristic findings called neurofibrillary tangles. So what are those? Well, those are a collection of tau protein inside the neuron cell body. So this is a normal neuron cell body here and another one here. But this one down here has this dark purple material right here, and that's that hyperphosphorylated tau protein forming a neurofibrillary tangle that you see in Alzheimer's disease. The symptoms of Alzheimer's come on slowly and insidiously, and most patients do not notice them. A classic board presentation is for the patient to be brought in by a family member who says they're getting more forgetful, but the patient themselves does not notice this. We diagnose it clinically, you can confirm it by autopsy, but there really is no imaging or blood test to prove someone has Alzheimer's disease. There aren't really very effective treatments for Alzheimer's, but some drugs have been shown to have limited benefit. One of these is memantine. It's an NMDA receptor blocker. NMDA stands for N-methyl-D-aspartate. It's a glutamate receptor, and this drug has some limited benefit in Alzheimer's. It's got some non-specific side effects like dizziness and confusion, and some patients have hallucinations. And then there are some acetylcholinesterase inhibitors which have been tried to boost the acetylcholine levels in the brain. These are drugs like donepezil and galantamine and rivastigmine, and these also have some non-specific side effects like nausea and dizziness and insomnia. And then there's some evidence that vitamin E may help by protecting against oxidation. Multi-infarct dementia is the second most common cause of dementia. It's dementia after patients have multiple small strokes. Patients who get this usually have vascular risk factors like high blood pressure and high cholesterol and smoking. They may have other evidence of vascular disease like coronary disease or peripheral vascular disease. And the key thing here, especially for your boards, is this will be a stepwise progression of symptoms. So patients will be doing okay cognitively and then have a disease like dementia. After patients have multiple small strokes. Patients who get this usually have vascular risk factors like high blood pressure and high cholesterol and smoking. They may have other evidence of vascular disease like coronary disease or peripheral vascular disease. And the key thing here, especially for your boards, is this will be a stepwise progression of symptoms. So patients will be doing okay cognitively and then have a sudden change and then another sudden change. And that's because they're having little strokes that make them worse each time. The only treatment for this is to make the risk factors better. You can't treat the dementia itself. A Lewy body is a collection of a protein called alpha-synuclein, and when it builds up in the brain, it can cause dementia or Parkinson's. To the brain, this process can go in a vicious
Pandit plan बनाएर पढिरहेको छु plan and read him. Planning is very essential. Okay, so indeed, writing and in my Sana. Oh, छ पढ्दिन यार आई वान्ट टु टेक सम रेस्ट धेरै बोल भयो पानी going to take now all the 0. It's like I have content and if it says 70, click 1, 2, 3, 4, 5, 6, quite impressive. So yeah. गर्नुपर्छ होइन त्यही भएर यता 10 बजी दर्शन रहेछ म खाजा खान्छु है आज high. No. Zoom out. भ्यू हो होइन pomodoro टेक्निकमा आमा खाइरहेको छु है आम सो सरी म बिरामी भएको छु सो खाइरहेको आम सिक दुध र पाउडर खाइरहेको म चाहिँ खासमा पढ्दै खानु ध्यान जान्छ नहुँदा नि होइन उज्जवल तिमी हेरेर आएको हो उज्जवल यसो हेरे भए च्याट बक्समा हेलो भन लेन्टी फोन त्यत्रो ठुलो हुन्छ ठुलो देखाएको यसमा लेन्टी फोन स्ट्रेट भनेको त काउडेट अपडामिन भयो लेन्टी फोन त्यत्रो ठुलो हुन्छ हामी 5 आवर्स पुग्न थालिसक्यो स्ट्रिम गरेको होइन भर्खर 1:38 AM भयो त्यही पनि आइएम भेरी फ्रेस दिउँसो सुत्दा त्यही बिराम भएर मजाले म दिउँसो स्ट्रिम गर्न पाएको थिएन 5 घण्टा गर्नुपर्ने दिउँसो जम्मा 2 आवर गऱ्यो त्यो पनि 1 आवर मात्र पढाइदिन्छु आफूले त्यो गबर त अझै होला 2-3 दिन लाग्छ होला त्यो पनि वेलकम ब्रदर मैले बुझेन यार कौडेट माथि परेर ठिक छ लेन्टी पनि तल हो गाह्रो रहेछ कुन भ्यू गऱ्यो Vertical. Okay. Intercerebral mass is equal to black. Okay. Last one. Okay. Nice. पुरै हो र यो होला ए नाइस द्याट नाइस बल्ल बुझ्यो नि मैले यो हेड भयो बडी भयो पुरै भयो है थाहा नबिर्छ मजाले अब कस्तो गराउनु पर्ने समात्न भने होला एउटा ठुलो दामी 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 हो दामी एकदम चाहिँ टर्निक्स बल्ल बुझ्यो त्यसमा क्लियर छ चाहिँ कति बेला ब्रेक भयो थाहा छैन मलाई ब्रेक भएछ है केटा हो 3 मिनट्स ब्रेक लिउँ पढ्न मजा आएको थियो मलाई ब्रेक लिन मन थिएन दिस pomodoro technique I should follow this टोटली होइन पढ्न छ केही चाहिँ प्रेसर छैन हामीलाई हामी पढ्न सक्छौँ है 5 घन्टा जस्तो सक्नुहुन्छ कि स्प्रिट होइन कोभिड निगेटिभ थियो भने किन थुलिरहेको छ बुझ्नु गाह्रो छ साथी Huh? This is wrong. This is wrong. आज घुसाएर आज यो हो 43 minutes ago perfect idea. Hello, stop. Hello. Session 5 starting. Let's go. Let's go. So Session 5, let's go. Study M. Study 20 from the insular region. जस्तै नानीहरू परिबाट एमएल तार्न चाहन्छ एन्जियोथेरापी त्यहाँबाट सिङ्गो त्यहाँबाट अनि प्रदान गर्छ सर्किट भन्छ काम छैन मतलब अब काम छ नि त्यति त्यो सोचले भने होला interesting, but yeah, frog. I don't keep damn. You don't see that weird stuff. Because mm, this is the actual representation, no? Yeah. Yeah, similar, yeah. Represent this. This is just the differences. Maybe, but yeah. And then the copy. Okay. धेरै पानी खाएको छ यार मैले आज is like a thumbnail clips. Yeah, because so you are the one. like 9 to 68, 7, 8, and we use sir. And let's go. And don't you? Okay, very bad. Cameras. Give me some. Sweet. High pyrogen plantain. 1 2 3 1 2 3 4 9 11 200 50 53 100 अनि 200 again त यो 100 पनि पुरा छैन ओके back to back 200 yeah I think I was prepared and enjoy good night hope भोलि पनि म यतिकै ठिक हुन्छु and now this training है viewers to concurrent को हेरेर छ I don't know 6 घण्टा भयो स्ट्रिम गरेको अझै राम्ररी मैले ध्यान दिन पाएको छैन है so yeah यसो त 3 बज्यो I want to go sleep night